Hello. Welcome to the AI for Net Zero webinar series. This webinar series is designed to bring together experts, innovators, and enthusiasts from both the artificial intelligence and sustainability domains. With an overarching goal to accelerate progress towards net zero targets, the series aims to engage and inform communities about groundbreaking research and developments at the intersection of AI and sustainability. The webinar series will explore diverse applications of artificial intelligence across various fields crucial to achieving net zero objectives, including energy, transport, environment, agriculture, and food systems. Today, our speaker is Dr. Erick Sperandio. He is an associate professor in AI for Clean Air Systems at the Surrey Institute for People-Centered AI and the program lead in AI and sustainability at the University of Surrey. He is a member of the Global Centre for Clean Air Research and a Sustainability Fellow at the Institute for Sustainability. With over 20 years of experience in clean air, air pollution, renewable energy, and smart manufacturing, he has led and contributed to R&D projects worth over £18 million. He has published more than 50 peer-reviewed papers, 7 book chapters, 50-plus conference papers, and holds 4 patents. Previously, at AI Climatech in Brazil, was the lead researcher at the Climatech Reference Center on AI, co-PI the Brazilian National Applied Research Center in AI for Industry, and PI of the NVIDIA Climatech AI Joint Lab. He also coordinated a key work group for Brazilian AI strategy. The title of his talk is Advancing Clean Energy Generation and Adoption Through Novel Sustainable AI Techniques. And with that, Eric, it's over to you.
Well, thank you, Danny, for your very kind introduction. It's my pleasure to be here today to present this work, as you just mentioned, entitled Advancing Clean Energy Generation and Adoption Through Novel Sustainable AI Techniques. So I'd like to, first of all, thank Michael Short, my colleague here at the University of Surrey, who kindly invited me to be part of this webinar today. And also Professor Ahmed, Sarah, and also Danny for your kind support and invitation as well. So I don't need to go through my introduction once again. So before we start this thing, I would like to first introduce to you the concept of AI and sustainability. Okay, so what AI sustainability actually means. So when we think about AI and sustainability, usually depending on your background, you might think this is about how to make AI development more sustainable, usually referred as sustainable AI or also sustainability of AI. And we might also think as this is how to apply AI to solve sustainability challenges or AI for sustainability. Actually, when we refer to AI sustainability, we actually mean these both sides of the same coin. So we have the sustainability of AI and AI for sustainability. In any case, we want to ask this very important question: how can AI contribute to achieve the United Nations, the Sustainable Development Goals? So if you want to do this, we need to put people in the environment at the core of AI development and also in its applications. So talking about the sustainability of AI, we have the things like model and data efficiency, trustworthy AI, how to tackle, identify, and mitigate bias and unfairness in AI models, how to improve model explainability, interpretability, also how to educate people and train workforce to avoid job disruptions and so forth. So it's about how to make AI development and deployment more sustainable. But at the other side of the same coin, we have the AI for sustainability. So it's about how we can develop and also apply AI techniques and solutions to enable us to foster the sustainable development, to tackle sustainability challenges such as clean energy, clean air, climate change, extreme weather events, health and well-being, smart manufacturing, and well, many more options here where we have. Also, this concept of AI sustainability also contributes to achieve the Industry 5.0 and Society 5.0 standards. So by putting the people and the sustainable development and the sustainability as a whole within the core of this concept, we can help the society and also the industry to achieve these standards, to make AI development more sustainable, and also to apply them to advance sustainability research and development. So for this, here at the University of Surrey, we have our two pan-university institutes, the People-Centered AI Institute and also the Institute for Sustainability. This program aims to bridge our two pan-university institutes together through this AI sustainability program. So at one side, we have the AI development at the core. So let me just highlight it here. Yeah, so I think you can see here the laser pointer. So at one side, we have the AI development at the core of its development, and how we can use AI and apply it and develop it to enable us to foster the development of more sustainable solutions in health and well-being, smart manufacturing, cities, infrastructure, homes, clean energy, air, water, entrepreneurship, weather forecasting, climate change, food systems, net zero as well. So this is about how we can develop AI solutions to tackle sustainability challenges, including clean energy and net zero. That is the main theme of our webinar today. But also at the other side, once again, we have at the core of the AI development area, we have the sustainability aspect. So it's embedded into every AI approach and development so that it is more people-centered and also more sustainable. So I'm talking about how to reduce CO2 emissions, how to train and deploy AI models more efficiently, how to make AI models much faster and more lightweight as well, how to reduce memory resources, and etc. How to make them more interpretable, explainable, and trustworthy, how to improve AI ethics, how to train people and educate people to work with AI instead of being threatened by AI. And then this is the overall idea of our AI sustainability program. That's leveraging our two pan-university institutes' expertise and leadership across these core areas. So for today, I want to bring to you some of our most recent works that we have been developing in AI and energy. So some of these works I developed previously in my experience in Brazil, where I was the lead researcher of AI in the CIMATEC Reference Center on Artificial Intelligence in Salvador, Bahia State. Bahia State has a size that's comparable to France and Spain in Europe, for example. So, for example, in this work that's published, you can see the link right below in the slide. This work was developed by our team, and the first author was our PhD student by that time, Pedro Zucatelli, who is now, of course, a PhD working in the energy sector. So this paper was about how an investigation on deep learning and wavelet transform to nowcast wind power and wind power ramp. So a case study in Brazil and Uruguay. So what we did here, we had access to anemometric towers and their measurements in different areas in Bahia State in Brazil here, in different sites with different climate patterns for each region. And also we had access also to data, anemometric data collected in Uruguay, right in the southernmost region, right below Brazil. So what we did, we developed a novel approach to embed the wavelet coefficients into the training of a deep learning model. And by taking the original wind speed time series, we applied the discrete wavelet transform and then we pass through the coefficients, the tail and approximation coefficients to the model. And then we predict these coefficients, then we reconstruct the wind speed time series to then enable us to not only predict the wind power, but also the wind power ramp. So for those who are not familiar with this, wind ramps are very important issues that the energy industry might need to be able to predict in advance to avoid harmful situations for wind turbines, and also to improve their predictability. So in this work, we could see that our model was not only able to predict accurately the wind power energy generation, but also the wind power ramps as well for those regions. So another work that we developed recently was a transformer-based deep neural network, also coupled with wavelet transform for forecasting wind speed and wind energy. This is also developed with one of my collaborators back in Brazil, MSc Thaleson Melo. So, and you're going to see that I'll be always here acknowledging the work of my collaborators and researchers, PhD or MSc students that have been collaborating and being part of my research group to develop this very novel research that I'm presenting right now. So here, what we did, we developed a novel transformer architecture. So for those who are not familiar with the transformer is the machine, or I would say the architecture, the deep neural network architecture behind the success of large language models such as GPT and Llama and so forth. So what we did here, we took the baseline transformer architecture and we modified it to be better suited to this type of problem, for multivariate time series problem, in this case for wind power, wind energy forecasting. And then we coupled it with discrete wavelet decomposition and selection. So as you can see, I pretty much like to work with wavelet transforms because they are very, very interesting. They are very, very powerful signal processing technique that can extract information not only from the frequency domain, but also from the time domain at once. So by applying them successfully, we have also developed before a technique to understand, to know which would be the best wavelet family in order to a specific time series problem. So we use this here as well. And then we apply this as an input to this architecture. And we also developed a special positional time encoding layer between the input and the multi-head attention mechanism, the transformer encoder of our approach. So this is based on sine and cosine functions that we apply to based on the frequency of the signal, and we apply this to the model as also part of the input as a feature augmentation technique. Then this architecture, we tested it also once again with real data from neurometric towers in Brazil, in the state of Bahia. And this work we published in the Energy Journal, and we were able to see how this would perform comparing to a fine-tuned LSTM architecture. That's, for those who are working with it, is quite famous recurrent neural network used for time series and sequential data problems. And we could see that our model not only surpassed the performance of the fine-tuned LSTM, but also achieved similar or superior performance when compared to state-of-the-art solutions, but taking less time to be trained. So this is very important to emphasize, because this architecture, when we use it to train a model like this for wind power forecasting, it takes less time and requires less computational resources to be trained. So it not only contributes for sustainability, in this case for clean energy, for the adoption, to foster the adoption and the use of clean energy, in this case to enable us to better predict wind power generation, as this is stochastic, because of the stochastic nature of wind because it's an intermittent energy source and not dispatchable as well. So it's very important for us to have the most accurate model to predict, but also that can run in an operational basis. And so this architecture, this technique can also not only achieve superior performance, but also can be trained in a faster way, requiring less computational resources and less time to be developed. So it also contributes to the sustainability of AI by bringing an architecture that is more lightweight, that requires less computational resources to be developed. So another work that we recently published and presented, this work was presented in IEEE Conference on Artificial Intelligence this year in Singapore. So here we developed a physics-informed neural network for handcasting wind components with globally available data sets. So here, this is a work that is being developed by my PhD student, Erick Santos, in Brazil, in Senai Cimatec. And here, what we did was we took a multi-layer perceptron neural network with the very same hyperparameters and architectures, but one was fully data-driven. So the first one was trained just with the data, but the other one was also has also embedded into it the physical knowledge about the problem. So what we did here, we applied a novel technique that is able to derive from the data the polynomial equations that can be solved by automatic differentiation of this framework that we are using here, to better understand the patterns, the physical patterns that are related to the formation and also to the wind phenomenon. So here we could see that our approach not only got increased performance, and when we compared with a fully data-driven multi-layer perceptron with the very same architecture and hyperparameters, the only difference was this physical knowledge embedded into the model, into its loss function, to better learn the patterns from the data. But also it comes with a drawback, because of course, by doing this, the time required to run the model got 5 times increased when we compare with the original architecture, the MLP. So, of course, because it requires more calculations here. But when we compare the inference time, they are quite equivalent. So it means that despite of they taking more time, they are more interpretable, and also they can leverage the physical knowledge that we already have about this atmospheric phenomena to better explain, to better interpret, and also to improve the accuracy of a deep neural network for wind power forecast, in this case, using a physics-informed neural network approach. So another work that we have recently developed, so this is the work developed by my MSc student, James Mendy, here at University of Surrey in the UK. He did a wonderful job by developing a physics-informed graph neural network architecture, this novel approach to wind power forecasting. So briefly speaking, what we did here, we developed a Fourier graph neural network, and we embedded into this Fourier graph neural network the physical knowledge, this famous power equation, to forecast wind energy generation. So then when we compare the results, as we can see here, our approach with only the Fourier GNN fully data-driven got interesting results. But when we informed it with the physical knowledge with this equation within the loss function of the model, we got superior performance when we compared with previous work like the multi-layer perceptron, the LSTM, even the transformer-based model that we just explained before, and the original Fourier GNN. We can see here at the right side that for the 6th hour ahead, when we compare the results with the predictions with the observed values, we can see that the Fourier GNN can have some good performance. But when we compare, visually speaking, qualitatively speaking, the forecast made by the Fourier GNN with physics informant. We can see that it can predict better the phenomenon by also predicting the spikes, which actually not well represented here in the Fourier GNN, the traditional Fourier GNN, meaning that it is not able to get the peak values. But our approach was able to achieve this, and this is because we developed this novel technique that is our physics informant Fourier graph neural network to better predict wind power generation. So other one that we developed, it was developed by my MSc student back in Brazil, Flávio Conterato. He already finished his master's there. So this was a comparison of the WRF solar numerical model so this is the weather research and forecasting model, the famous one that is the state-of-the-art physical numerical model to simulate regional weather events and patterns, but a specialized version of WRF model for solar applications. So we took, by that time, the most up-to-date version of WRF solar, and we ran it for specific scenarios. And then we compared these simulations with the physical numerical model with deep neural networks to forecast solar photovoltaic energy generation up to 48 hours ahead. So once again, we did it for by state. As you can see, I work a lot with data and use cases by state, not only because I'm from Brazil, but because this state is a very special one because it has one of the biggest potential for renewable energy generation in Brazil. And this region is special, is one of the biggest regions in Brazil with the largest potential for solar power generation. And then, so just to explain this better, so we took data from these 4 different cities here, and we tested our model with unseen data for this specific city here in the middle of this region, but also we test our model in another city far away from those cities that the model was trained with. So then we compared our results, and we could see that not only the models got our best model, that was a multi-layer perceptron, fine-tuned for this task, got the best performance metrics, but also it was trained with around 10 times less the time required to run the simulation in WRF solar. But the point is, just for training time, for inference, the time is even much, much lower than this. It's like a fraction of the time required to actually train and even run simulations of a numerical model. So it's quite interesting to see how AI can play a key role to improve our capacity to better predict such variables like atmospheric variables to enable us to better predict the weather, the wind, and solar radiation, cloud formation, etc., but with a fraction of the time required to run the traditional state-of-the-art numerical models. They can definitely be used as a way to complement these state-of-the-art solutions, or even be used as the means to enable operators and decision makers to run operational forecasts much more faster than traditional state-of-the-art solutions. So in this case, another project that we worked with was in simulate the hydrogen production through an AI-based surrogate model for proton exchange membrane water electrolyzer. So this was a great project developed by my MSc student last year, Harjit Singh. He already finished his master's here, University of Surrey as well. And with the partnership with my PhD student, Mohammed Basir. So what we did here, we took 2 different types of data sets of proton exchange membrane, real-world data from proton exchange membrane, and we developed an AI surrogate model based on a multi-layer perceptron by taking this data and then to simulate how the model would behave to simulate the production of hydrogen. So now we also developed this web interface that allows one to simulate the production of hydrogen by inputting the specific parameters of a proton exchange membrane water electrolyzer to input to the model, and then to predict the production of hydrogen. So this is also providing a wonderful ground and the stepping stones for us to keep working on our research activities here, for example, on the optimization and prediction of the production of green hydrogen from hybrid intermittent renewable energy sources. So we are right now working tirelessly on this research project as well. So a very recent project that we also have been working with. So for those, I think I did say this before, but I have a background in computer science, and I have been working a lot in how we can develop novel solutions, computational solutions to tackle sustainability challenges, and also how to make them more sustainable. So that's why I am also the lead of this AI sustainability program here at the University of Surrey. So in this case, we are working on quantum artificial intelligence, in this case, quantum neural network model for wind speed forecasting. So we are leveraging the concept of quantum computing. So, for example, using the concept of entanglement, qubits, and also the superposition characteristics of a qubit to create a novel quantum neural network that is able to predict wind speed and hence wind power generation for 1 hour ahead. So this is the first work doing this. It's a work that we are developing. It is being developed by my PhD student Otto Pires in Senai Sematec in Brazil, which is also doing a wonderful job in this work. And we are also moving forward fast in also developing more quantum AI techniques and solutions for sustainability challenges. Why? Because, of course, we believe that in the near future, we're going to have quantum computers available so that we can run them for operational purposes, and not only for the industry, but also for the society. But once they are available, they can be run in a very small fraction of the time today required to run traditional, conventional artificial neural networks for classical computing. So that's why we are preparing ourselves for this very near future by developing these novel cutting-edge techniques based on quantum computing, in this case, to better predict wind power forecasting. So another work that we recently also developed, this is a work developed by MSc student here, also University of Surrey, Noah Gibbons, which did a really great and wonderful job. We took data from Aero5 from ECMWF, and we developed a series of tests to see what would be the best deep neural network architecture to forecast wind, wave, and solar energy generation in a specific site located in an offshore base outside of the UK. So here we took several input variables from Aero5, and our target variables were wind, wave, and solar variables. I am not going to the very details right now, but we have specific variables related to wind, like wind 100 meters and V 100 meters, components of the wind, and wave and solar radiation and cloud formation, etc., air temperature. And here we test these 6 different architectures. So the traditional LSTMs, convolutional neural networks, and also a hybrid CNN LSTM model. And we also compared with our previously published transformer model. And also we compared with a Mamba architecture that is the first one doing this for wind power forecasting, by the way, wind, solar, and wave, to be more precise. And also another very novel architecture, the Mamba former. And also what we did here, it was really great to see, because usually we know this empirically, but no one ever did this kind of evaluation before. We took the data and we shuffled the data to train the model. Then we unshuffled the data with just a sequential data to train the models. And what we found was that the best model, the best architecture to predict wind, wave, and solar for the next 24 hours ahead was the transformer. As we can see here, not only by the highlighted in bold metrics here, and in this case, the normalized mean squared error and Pearson R, but also if you can see here, the metrics. So as the forecasting horizons evolve from 1 to 24th, from the first to 24th hour ahead, we can see that transformer architecture achieves the best metric and is also much more stable than the others, because the others, although their metrics are better at the beginning of the first hours of the forecasting horizon than the transformer, they start to degrade once they look much forward in the forecasting horizon. In this case, it is the normalized mean squared error. So the lower, the better. In the other case here, it is the coefficient, Pearson R correlation coefficient. So the bigger, the better here. So once again, the same behavior we can see. So the higher, the better here. The very first hours, the other models got better results, but they start to degrade very quickly. But the transformer kept very stable performance, and we compare with the others. So highlighting how that transformer-based architecture is really, and still is, the best approach for this kind of modeling problem. In this case, for hybrid offshore renewable energy forecasting. So other work that we have been working with is on how to optimize hybrid renewable energy generation using artificial intelligence. So once again, this is the work have been developed by my MC student, Oa Gibbons, and also by my PhD student in Brazil, Dalton Filho. So we are working on, okay, so as we have more than one renewable energy source, but given that they have this intermittent nature, how can we optimize the total energy throughput of a hybrid renewable energy power plant so that we can avoid a situation where we don't have to burn any fossil fuel, for example, to be totally relying on renewable energy sources. So, for example, and here we did some simulations considering a battery system, also considering solar, wind, and wave energy generation sources. And we did some simulations for different periods of the year that were unseen for the model during the training phase. So in this scenario, for example, the below one, we can see that by doing the optimization, this is the synthetic generated demand curve. And we could see that the optimization system was able to get the best of the hybrid renewable energy sources without the need to burn any kind of fossil fuel to meet the demand. But at this other scenario, we could see that there was a moment where we didn't have enough renewable energy supply to the grid. And even with the battery, it was not able to also hold the system altogether. So it needed to, in this case, in this simulation scenario, it needed to burn some fossil fuel to complement the energy throughput, the energy output of this system. So it means that, for example, there are some opportunities here to run other types of simulation scenarios to see, for example, if we improve the capacity of this hypothetical hybrid renewable energy power plant to harvest more energy from the wind, from the waves, and also from solar, because solar here is playing a very modest role in generating energy. So then we could see that there would not be any scenarios where we would need to complement the energy generation by burning fossil fuels, which is what we want. We want to achieve net zero. We want to fully rely on clean energy. So we can use AI to generate these scenarios and to optimize the whole system towards this direction. And at the other side here, we can also see another simulation where we can see the state of charge of a battery system against the cumulative energy and the energy price. So in this case, we want to not only optimize to maximize energy throughput of a hypothetical hybrid renewable energy power plant, but also we want to maximize the income of this renewable energy power plant so that it can be not only more sustainable, but also economically more feasible, more suitable, so that we can actually, in practical terms, foster the adoption of clean energy by energy suppliers and also by the community, by society as a whole. So this is really key here to state that AI can play a key role for us to enable us to achieve these goals. And in this case, also in the UK. Another work that we also have been developing, and just moving towards the end right now, was developed by my PhD student Mohammed Wazir, which did a wonderful job here. We developed an intelligent, optimized deep network that was based on a red deer optimizing system, where we are able to extract the main features from a wind turbine SCADA database, and then to develop a specific neural network that is relying on this red deer optimization system to better forecast the wind. So we test this approach with other type of machine learning models, and our proposed approach achieved a superior performance here for wind power forecasting. This is also a paper that we recently published as well. Also, moving towards to the end of this presentation, I know that's too much to digest, but I hope this can be useful for every one of us that are working on these areas of AI, clean energy, and net zero, AI for net zero in this case. We are working as well on AI for extreme weather events. And why energy here? Because as you can see in the case of lightning strikes play a very important role in how they can be harmful, I would say, to energy distribution systems. So distribution lines across different regions. So if you know in advance if that region is more likely to be struck by a lightning event, then you can prepare yourself in advance to make some measures to avoid any more damages to the system or to the people that rely, or the industries, or anyone else that rely on that power system. So here we developed a deep neural network to forecast lightning strike events with 6 hours in advance. So we are also finishing this work. We have right now, our results are achieving this the superior performance than compared with state-of-the-art solutions, and we are relying totally on public available data sets. In this case, the data from the global data simulation system that is provided by NOAA in the US. Another work that we have been developed also is related to smart manufacturing and how AI can help the energy sector to be more resilient. So it also contributes to achieve sustainable development goals related to making the industry and the society and the cities, etc., more resilient and smarter. So in this case, we are working on predictive and prescriptive maintenance of wind turbines. And this is a work that has been developed by my PhD student, Rogério Santiago, in Brazil as well. And we have been working on the development of this prescriptive maintenance models to better predict when and how a failure will take place in a wind turbine, but also what measures need to be taken to avoid or to mitigate their failures. So, for example, we developed this work that we published to classify faults and rotating machinery in the industry using specially designed one-dimensional convolutional neural network to better classify faults in industrial rotating machinery. Also, it's important to emphasize in those cases where we cannot, when we still need to burn fossil fuels to generate energy, we need to also account for their emissions and also to predict them, their impact in the atmosphere and also in people's lives and in the environment as well in advance. So here we developed a methodology based on deep neural networks within our Global Center for Clean Air Research here in the University of Surrey, that's run by Professor Prashant Kumar, which is the founding director of the GCARE. We use data from 2 different sites here in the Guildford city to develop a bespoke and novel hybrid deep neural network based on 1D CNN and LSTM to better forecast the next 24 hours ahead of the concentrations of particulate matter below 2.5 micrometers. And also to finish, it's also important to emphasize the sustainability of AI aspect. So when we have, thinking ahead, when we have these many models available to better predict the wind power, solar power, wave power, and many other types of clean energy sources, they must be run in a more sustainable and efficient way. So this is also about how we can make these models more sustainable. So we need to think ahead. We need to embed the sustainability part within our AI development since the very beginning. So in this case, we are developing this project where we want to take these very large deep neural network models that are so good in doing their job, but still they can be quite big if you want to put them to be deployed near or at the edge. So here we are exploring techniques, and we developed a special technique that's able to reduce the size of an original model like this one in this case, for predictive maintenance in the industry. And we compared our technique with other compression techniques available in the literature. And our model that was developed for a knowledge distillation approach achieved good performance, just a very small decrease in the overall performance, but a very large decrease in its size when compared to the baseline models, and even with the other compression techniques. But the time required to run this model was also pretty much increased and improved here, as we can see in this table. This work was also published and presented in the last IEEE conference on AI in Singapore. So we have some ongoing projects. So, for example, we are working on multimodal physics-informed foundation models for time series forecasting of atmospheric phenomena. Also, PINNs for weather, renewable energies, and air pollution forecasting. So, as I said before, AI for optimizing green hydrogen production powered by intermittent renewable energy sources, and also AI for nature-based solutions to mitigate urban heat and air pollution, the prediction of extreme weather events using deep learning, prescriptive maintenance of wind turbines, cause inference trustworthy AI, and last but not the least, quantum AI. Thank you so much, and I hope this can be useful for our audience. Thank you.
Well, thank you very much, Eric, for a splendid talk. We have plenty of time for questions, and the first one has already been added to the chat, so I'll read that one out to you first. So this is from Sarah Perez. How can we ensure the data sets used for training AI models are ethically sourced and representative, whilst considering the impacts of data collection and processing in relation to sustainability?
Wow, that's a very tricky question, by the way. Thank you, Sarah, for your very wonderful and insightful question. Yes, definitely there is a challenge in ensuring that these data sets are ethically sourced and representative. Of course, usually when we talk about clean energy, specifically speaking here in our context here, we usually don't have to be worried about, for example, sensitive attributes like gender, race, religion, etc. That are more related to, I would say, human sensitive attributes. But I have been working a lot in this area of trustworthy AI. And in this case, one of the main concerns are related, for example, about the privacy of the data. Usually, people, companies, etc., don't want to, or are not willing to make their data sets available. And yet we need to train these models. So usually we need to work on techniques that are not where we can anonymize the data, or, for example, normalize the data to avoid any kind of information that is passed through the chain to possible competitors, etc. But also dealing with regulations like the GDPR and recently launched the European Union AI Act. So, and also we need to account for data uncertainty. So this is also another very important aspect when we work with data for this kind of problems, you know. So when we work on data collection, usually we need to be aware of how the data was collected, from which sensors, who was able to do it. So, if the data was curated at all by someone else, and if not, what would need to be done to curate the data, to pre-process data, to enable it to be fed into AI models. So once again, there is a lot of things we can discuss here. Not so sure about the time we have, Danny, but this is definitely a very important point.
Thank you. Well, that was the only question posted in the chat so far, although please do post your questions. I have a couple if nobody else wants to jump in. I think the first, I was struck by how many different projects you have in the arena, and how many of your students and collaborators are essentially fitting different neural network and transformer type structures to do prediction and to judge that prediction as being good if the RMSE is good and the Pearson's correlation is high, and so on. When it comes to ethics, those predictions don't have uncertainty on them. And it might be that they might be those predictions when they're in the environment, particularly for wind power generation or something like that. Some decision maker needs to know. So what's the probability that we exceed or drop below your prediction, for example? So yeah, not this one. I think the later one where you're doing the physics-informed neural networks. That would be a good example.
This one here, for example.
Yeah, so I guess my questions are round the houses. Showing what's the bar, do you think, for in terms of ethics and predictive skill, and is uncertainty involved in that at all?
No, that's a very important and very wonderful question. Thank you, Danny. Actually, this is really important. In this work specifically, I'm not showing here the prediction intervals related to the uncertainty of the model, and whether this champion model is statistically different from the previous one. So, but for example, I can tell you that's something that we definitely have been working with. So let's just come back a few slides here. So for example, this work, because it's here, I can show. So in this work, it's also available. You can read the paper. We actually calculate the uncertainty here to showcase whether the model will be trustworthy or not to do the forecast. Of course, there are always uncertainties related to those forecasts. They are not just pinpointed values, discrete values that are just provided by the model. We need to quantify and to develop some uncertainty-aware procedure. So in this case, we quantified the prediction intervals, the uncertainties, and also we assessed whether this model is statistically different from the baseline or the models used to compare with. So we use, for example, a technique like Cox-Stein rank test to assess this. So this is definitely a very important point. And for each work, I would say every time I'm reviewing a paper that is provided this kind of technique, I'm always wondering and asking actually the authors to provide this kind of assessment. Otherwise, we cannot say if this model is really good or not, if they are not, for example, statistically different from each other, or their predictions intervals are too wide, right? So it's a very important point. So we have been accounting for this. And well, some of this work, of course, are still to be submitted. If not, if they are not being submitted very, very shortly, but they will be definitely this kind of assessment will be there for sure.
Okay, thank you. Quick glance at the chat. No other comments yet, but something may occur to somebody in a second. I had another question on this topic. So I think it's on the next slide. You have the performance of this system, the transformer with wavelets versus the LSTM. Yeah, okay, that's it. It's probably quite a naive question compared to the last one. My understanding of LSTMs is they're kind of like time series models that are able to see longer in the past. So they probably compare with ARP models where P is larger than 1 and so on. And I probably know enough about wavelets, so they're kind of like local smoothers, and you've used a low and high pass filter, right? So in a sense, is your wavelet model seeing the future a bit more than the LSTM when it's fitting the time series and training itself? Because, like if you were to fit a principal component model to a time series, all the statisticians will go, wait a minute, you're using the future to train that. You're using the future to train a model that's going to then predict the future. And wavelets is going on less of an extent, right? Because it's a bit more local.
Yeah. But your question is very important, by the way. Usually people do not ask this kind of question. So usually when people work with wavelet transform and other kind of signal processing techniques, they are not pretty much aware of the need of removing the future from the sample that is going. If you want to predict the future, you cannot look into the future to build the coefficients, of course. So here we made sure that this technique, we are not looking at the future. We're not using data in the future for a specific sample to compute, to extract the coefficient, the detail and approximation coefficients for the wavelet transform. So we have been working a lot with this, so we are pretty much aware of this problem to avoid this kind of situation. So this answers one of the questions. The other about, I'm not so sure if it was a question but or a comment, but about the LSTM versus transformer. They both are meant to be more suitable for sequential data, right? But transformers have been quite more successful than LSTM models, depending on in various applications, because they not only are able to better predict short, medium, long-term dependencies by leveraging the multi-head attention mechanism that's built within them, but also because they are much more parallelizable than the LSTM model. So, for example, if we take the same amount of resources, I mean time and computational resources, and we train, and we try to make LSTM model and to fit to train an LSTM model and to train a transformer model, we can feed more data to the transformer model with the same computational and time resources. So it means that the transformer can also see more patterns, more data than the LSTM, because it's more efficient than the LSTM architecture. So those two main aspects I would highlight here to emphasize why the transformer is not only more successful in natural language processing applications, but in this case here, to better predict multivariate time series data, in this case for wind power forecasting.
Well, thank you. I definitely feel that those couple of questions raked you over the coals a bit. Ahmed, do you have any questions?
Yes, thank you, Eric, for the very interesting presentation. It's impressive and extensive work. I have a question mainly about extreme weather events and training data required in this case, and what kind of data preparation you need to make this model work.
Oh yeah, that's actually one of the most interesting questions, because when we work with extreme events, not only extreme weather, but also, every sort of extreme or rare event, we need to enable the model to see this pattern, despite of having much more examples of the other situations or events or classes, for example. So the same, usually long short story, usually what we do is to try to make the less represented class, the more represented class to be lowered down to a comparable number of samples for the less represented class, so that we can enable the model to see more examples. So, for example, in this case, we have around less than 1% of the whole set of data that we have here corresponding to lightning strike events. So how to overcome this challenge? So we train our model in a novel way so that we could see not only the lightning strike events, but also the normal situations in a more balanced way. And also we did some how can I say, modifications in our methodology to make sure that our model learned this successfully. So then we applied it an unseen period, and this model achieved superior performance than the current state of the art. So in this case, we use data from the GDAS system, from the Global Data Simulation System that is made available by NOAA in the US. And also we use data from the National Institute for how can I say in English? It's INPE Institute in Brazil, that kindly provided us data about lightning strike events for this period, for this whole region in the state of Bahia in Brazil.
I think we've got time for a quick question from the Relations Company on YouTube. And they ask, have you found inconsistencies or conflicting outcomes between the models?
Always. During the development, of course, when we publish a paper, when we present the research, we are always presenting the most advanced results that we got. But when we are developing the research itself, considerable amount of the time that we are spending on it are dealing with this kind of conflicts or conflicting outcomes that we can see in the models. For example, sometimes we're developing different sort of models, and we can get a better model that's achieving superior performance. But when we assess whether these metrics or whether this model is different from the other models, we cannot guarantee that they are different statistically speaking. So because of it, we cannot say they are better than the other models. So this is one thing that we usually face, among other things. Sometimes we're just facing a problem where the model is suffering of vanishing gradient problem. So, for example, this research here in AI energy and extreme weather events that was developed by my former MSc student, Mirella Araújo, which already finished her MSc, which did a wonderful job, by the way. We faced lots of difficulties on how to deal with data, as Ahmed just mentioned here, and also the models that we tested and developed as well. And at the beginning, the models were not able actually to predict any lightning strike at all. So we spent a lot of our time trying to achieve this, and finally we got it.
Okay, thank you. So it's 2 minutes to Ahmed. Do you have any final questions? There are no more in the chat.
Thank you. I think let's check
okay.
the chat again.
Yeah, I'll just check the chat. No, it's clear. So with that, I'd like to thank, on behalf of the AI for Net Zero webinar series, Dr. Erick Sperandio for a wonderful talk with lots and lots of really, really interesting methods and applications that we've seen today. I'd like to close with a couple of announcements. So the AI for Net Zero conference. So additionally, on behalf of the UK RI AI for Net Zero program, we'd like to highlight an upcoming conference, AI for Net Zero, Accelerating the Net Zero Transition with AI. So that's going to take place from the 16th to the 19th of December at the University of Exeter. There'll be a 4-day event that brings together leading experts and high-profile speakers to discuss how AI can drive meaningful progress towards achieving net zero by 2050. The abstract submission deadline has been extended to Thursday, the 17th of this month, and we're currently accepting contributions for talks and posters that explore the role of AI in addressing net zero challenges. More information is available through the link that's been shared in the chat. And then finally, I'd like to announce our next session in this series. So our next session will take place on Tuesday, the 15th of October at 2 p.m. This session will feature 2 early career researchers who will share their work in the field of AI for net zero. Firstly, Dr. Andrew Mole from Imperial College London will present AI-controlled wind farms, Bayesian optimization and reinforcement learning. And then Dr. Gavaz Opong from the University of Leicester will present Unlocking the Secrets of Soil, Predicting CO2 Emissions from Arable Peatlands Through Microbial Insights. Once again, everyone, well, we can't thank Erick because everyone's on YouTube. So I will thank Erick, and Ahmed, I'm sure you will as well.
Thank you, Erick, for joining us and for all the insights.
And until next week, that's goodbye from us.
Thank you so much once again for this very wonderful opportunity. I wish for you all the best and all the success in your journey, in your mission to achieve net zero through AI. Thank you so much. And looking forward to collaborating to keep contributing to your initiative.
Thank you.
Thank you.